Let's talk about oxidation reduction equations, otherwise known as redox. We can identify them and we can balance them. Why don't you try to turn off the machine here and try to balance this equation by inspection by going right, left, and so forth. Take a couple of minutes to see about doing that and then turn the system back on. This is not an easy equation to balance. There's 3 reactants and 4 products. And clearly there are other anions that are going to be involved with the hydrogen ion, the potassium, and the manganese ion. So how on earth are you supposed to balance that? And how many days will you allow for the next test? You can balance the chlorine. Well, you need 3 on the FeCl2 on the left and then 2 on the FeCl3 on the right, but then that doesn't balance out the iron. Well, that's just a start. This is a mess by inspection. So let's talk about identifying redox equations. We know it's not an ion swap like precipitation. For example, the one that we talked about in the ion swap slides, lead nitrate with sodium iodide. The lead reacts with the iodide to form a precipitate, yellow precipitate of lead iodide. Lead was dancing with nitrate, runs into iodide, and elopes. It forms a permanent solid that the water can't break up. The sodium and nitrate are left in solution. But there's no change in the oxidation state. This lead starts off as +2 and it ends up as +2. It's not an ion swap as an acid-base reaction either. For example, hydrochloric acid with sodium hydroxide, an acid-base reaction. There is no change in the oxidation numbers. The sodium ions and chloride ions, the hydrogen ions and hydroxide ions start. The water is formed, but the hydrogen still hasn't changed its oxidation state, and nor has the hydroxide. They just stuck together. So, to be certain what kind of reaction you have, we assign oxidation numbers. You actually probably already know how to do this. You just don't know that you know how to do this. Oxidation numbers are a bookkeeping device for chemists. We assign oxidation states to elements in compounds or free elements according to specific rules. They may not, and often don't, correspond to the atom's real chemical situation. A bonded atom's oxidation number is the charge it would have if the electrons in the bond were assigned only to the more electronegative element. In other words, we are treating covalent bonds as ionic bonds and giving the electrons to the more electronegative element. So let's look at the rules. Monatomic ions have the same oxidation number as their charge. So Na+, the oxidation number is +1. Fe2+ is +2. Cl- is -1. See how easy that is. Hydrogen ions are always +1, except in the rare cases when they're bonded to metals like sodium and are hydrides, then they're -1. Oxygen is -2, except in the rare case where it's a peroxide like H2O2, then it's a -1. And elemental substances are always going to be 0 oxidation number. For instance, oxygen gas here, or sodium metal, or aluminum metal, or phosphorus, the nonmetal, if they're the pure element, then the oxidation number is 0. For any neutral compound, the sum of all oxidation numbers in the compound is 0. So for carbon dioxide, if we add up the oxidation numbers for carbon and oxygen, they add up to 0. There's got to be equal pluses and minuses. For a polyatomic ion, the sum of the oxidation numbers is the same as the ionic charge on the ion. For instance, in the ammonium ion, the sum of the oxidation numbers must be +1. And if the hydrogens are all +1, then that means the nitrogen, think about it, must be a -3 in order to leave that plus charge. For permanganate, the sum of oxidation numbers is -1, and if the oxygen's -2 here, and there's 4 of them, That means the manganese would have to be +7. Why don't you do some here for all these atoms? Ozone is an allotropic form of elemental oxygen. Therefore, it must be 0. Hydrogen bromide. Hydrogen's +1, bromide's -1. Very sensible. But how about Br2O? Remember, we're going to assign all the electrons to the more electronegative atom, which is oxygen. So the oxygen is almost always -2, and as an ion it is. So the bromine here must be +1. So different atoms can have different oxidation numbers. Oxidation numbers may change. When in doubt, look at your periodic table. Periodic table's position of the element will be helpful. Now a few more difficult ones. Well, that wasn't so hard. Higher oxidation state. Here we have to do the chromium and the oxygen, but the oxygen is -2. With 4 of them, you have -8. And 2 of those negative charges peek out of the chromate ion. So the oxidation atoms that are balanced off by the chromium total -6. The chromium here must be hexavalent, +6 oxidation state. Here you see how that works. Now determine the oxidation numbers of each element in these compounds. And check your answers. So the oxygen here must be a peroxide oxygen, -1. Sodium is never anything but +1, or if it's an element, it's a 0. Now, in a redox reaction, at least 2 elements must change their oxidation number. One's oxidized, the other's reduced. So let's look at one we understand from the lab. We remember that silver nitrate reacts with copper metal to form silver metal and copper 2 nitrate solution. Here's the net ionic equation. Ag plus copper metal, that should say solid, gives us Ag and copper 2+ ions. The ions are aqueous. We assign the oxidation numbers according to the rules and take a look and check to see. Now we determine half reactions. The half reactions are separate oxidation and reduction reactions. We separate the oxidation from the reduction and we put electrons where they go. For oxidation, they're going to go on the right as a product, and for reduction, they're going to go on the left as a reactant. And so we can see the Ag +1, you add an electron to form Ag0. See how these charges balance off, +1, -1. The copper metal is oxidized to copper 2+, giving away 2 electrons. Now that we have the half reactions, and we know that the silver is produced by reduction, the copper 2+ is produced by oxidation. We balance the half reactions with each other. We can't give away fewer or more than we take in. So we find the lowest common multiplier that gives the same number of electrons given and taken. And in this case, we're going to multiply the reduction reaction by 2. So that we're producing and taking 2 electrons for each of the atoms. And there is your balanced reduction reaction. We can then add the 2 half reactions to get the complete reaction, and it is balanced. And shows the 2-to-1 ratio of silver to copper that you're familiar with from the lab. Now try this one. Turn off the video while you're doing it.